Hi friends, welcome to the lecture of linear algebra. In last lecture, we have seen what is how to represent the transformation by using the matrices. Now we have to see in today's lecture we have to see what is a row and column rank of a given matrix. Row and column rank of a matrix. Okay. Now we have to see what is a row and column rank of a matrix. Let A be a and M cross N matrix over the field F over the field F. The the row vectors of A are the vectors alpha 1, comma alpha 2, comma up to so on alpha n, which are belonging to Vn over F defined by each alpha I equal to AI1, AI2, up to so on AIN, where i's lies between 1 and 2. No, that is a range of i's where i's lies between 1 and 2. No. Okay. So, if A be any matrix of order m cross n, then the row vectors of the matrix A are the vectors alpha 1, alpha 2, up to so on alpha n belonging to Vn over F, defined by each alpha I is nothing but AI1, AI2, up to so on AIN, where I lies between 1 to F. And the space spanned by the vectors alpha 1, alpha 2, up to so on alpha n is called row space of A, is called row space of matrix A, and it is subspace of vector space Vn over the field F, and the row rank of A, the row rank of matrix A is the dimension of row space of A. So, if we have given one matrix A which is of order m cross n, then the row vectors of the matrix A are the vectors of the form alpha I, where each alpha I is nothing but AI1, AI2, up to so on AIN, and the space which is spanned by the row vectors alpha 1, alpha 2, up to so on alpha n is called a row space of A, and it is a subspace of a vector space Vn over Vm. Actually, there is a linear transformation which is from Vn over F to Vm over F. So, and the rank of matrix A is nothing but the dimension of that row space of B. And this is the row rank of a matrix. Now we have to see what is the column rank of a matrix. Let A equal to Aij be an M cross N matrix over the field F, over the field F, Then the column vectors of A are the vectors beta 1, beta 2 up to so on beta n belonging to vector space Vm over here defined by defined by each beta j is running from beta j consists of a1j a2j up to so on amj where j is like between 1 to n. Okay, so these are the row column vectors of the matrix A, and the space spanned by the space spanned by the vectors beta 1, beta 2 up to so on beta n, beta 2 up to so on beta n is called column space of A. Called column space of A. As each beta 1, beta 2 up to so on beta n belonging to Vm over here, therefore it is the subspace of Vm over here and is subspace of Vm over matrix M. Now we have to see what is the column rank of that matrix. So the column rank is nothing but the column rank of matrix A is the dimension of column space of A. Column space of okay. So this is the column rank of a matrix A. Now let us see in general what is the row and column rank of a matrix. If suppose A be any matrix of order m cross n, that is, suppose this one is the matrix A. A11, A12, up to so on, A1n, A21, A22, so on, AM1, AM, so on, AM. So this is the matrix of order m cross n. Now we have to find out the row and column rank of the matrix. If suppose this one is the first column, let us denote this by beta 1, sorry, alpha 1, alpha 2, so on, alpha n. And these are the beta 1, beta 2, so on. This one is the beta n. Now we have to find out the column rank and row rank of a matrix. Then the row rank of matrix. These are the rows. First row beta 1, second row beta 2 up to so on beta m. So rows of matrix A are nothing but beta 1, beta 2 up to so on beta m, and each beta m is of the form AI1, AI2 up to so on AIN, that is A11, A12 up to so on A1n. It is for each I running from 1 to m. So this one is the subset of your Vn over here. Since each beta I contains these n elements AI1, A11, A12 up to so on A1n. These are the n elements. As each beta 1 is in form of n elements. Therefore, this one is the subset of Vn over here. And column rank contains the elements alpha 2 up to so on alpha n. And each alpha I is of the form A11, A21 up to so on AM1. Therefore, it is a subset of VM over. Yep. Now, in actually, row rank of a matrix A is nothing but the number of linearly independent rows in the matrix A, and column rank of a matrix is nothing but the number of linearly independent columns in the matrix A. So, this is the row and column rank of a matrix. Simply, row rank of a matrix is nothing but the number of linearly independent rows in the matrix A, and column matrix of A is nothing but the number of linearly independent columns in the matrix A. Now, there is one theorem. Let A be any m cross n matrix over the field F. Then the row rank of A of matrix A is equal to the column rank of, that is, if A be any matrix of order m cross n, then we have to prove that the row rank of a matrix A is equal to the column rank of a matrix A. Okay. True. Given that AB and m cross n matrix over the field F. Now, let beta curly beta equal to E1, E2 up to so on En, and curly beta 1 equal to E1 dash, E2 dash up to so on Em dash are the standard ordered basis. Standard ordered basis for vector spaces Vn over F and Vm over F respectively. So, curly B it contains n elements E1, E2 up to so on En, and curly B1 contains E1 dash, E2 dash up to so on Em dash. These are the standard ordered basis for vector spaces Vn over F and Vm over F respectively. Now, let T be as linear transformation from vector space Vn over F into Vm over F such that A be the matrix of T relative to order the basis B and B1. Okay, therefore from this we conclude that T of some x1, x2 up to so on xn equal to y1, y2 up to so on yn, where each yj equal to where yj is equal to summation j running from 1 to n aij of xj and I lie between 1 to n. Okay. So T be a linear transformation from vector spaces Vn over F into Vm over F. And in previous lecture, we have seen that if T be a linear transformation from vector spaces Vn over F into Vm over F, such that A be the matrix of T relative to V and V1, and we have find out the matrix of linear transformation T transpose, that is T to the power T relative to ordered basis V1 star and V star. Okay. Now from this, as T is linear transformation from vector space Vn over F into Vm over F, then T of x1 x2 xn will be equal to some y1 y2 up to so on ym, where each yj is of the form summation j running from 1 to n aij of fj, I running from 1 to m. Now we know that T of E1, comma T of E2 up to so on T of En spans the range space of T, spans the range space of linear operator, that is linear transformation T. Now also T of E1, T of E2 up to so on T of En are the column vectors of the matrix A, are the column vectors of matrix A, as these are the column vectors of A, and we know that the space spanned by the column vectors of A is called the column space of A. Therefore, these n vectors T of E1, T of E2 up to so on T of En spans the column vector of A, spans the column space of A, which implies T of E1, T of E2 up to so on T of En are the spans the column space of matrix A. Okay, so T of E1, T of E2 up to so on T of En spans the range space of T, and T of E1, T of E2 up to so on T of En spans the column space of A. Then the range space of T is nothing but column space of A, column space of matrix A. Now, range space of T, dimension of range space of T is equal to dimension of column space of matrix A. Now, dimension of range space of T is nothing but the rank of the matrix T. Rank of the linear transformation T. So it is the rank of T, which is equal to, and dimension of column space of A, according to definition of column rank, dimension of column space of A is nothing but the column rank of matrix A, which is the column matrix. Column rank of matrix A. Column rank of A. Take this one as equation 1. Now, as B and B1 are the standard basis of Vn over F and Vm over F, then let B1 star and B star be the dual basis of V1 and B. We have given that B and V1 are the basis of vector spaces Vn over F and Vm over F. Therefore, V1 star and B star be the dual basis of V1 and V1. Let T to the power T is a transpose of linear transformation, from vector space Vm star over F into Vn star over F. Then the matrix of linear transformation T to the power T relative to relative to ordered basis B1 star comma B star is A to the power T, that is A transpose. Since in previous lecture we have proved that if Vn and Vm be two finite dimensional vector spaces over the field F, and B1 is the ordered basis for vector space V and with dual basis B star, and B1 be the ordered basis of vector space Vm with dual basis B1 star, and A be the matrix and T be any linear transformation from vector space Vn to Vm, then A be the matrix of T relative to ordered basis BB1, and B be the matrix of linear transformation T to the power T, that is transpose of linear transformation relative to ordered basis B1 star and B star. Then we have proved that B is nothing but the A transpose. Therefore, that theorem, the linear transformation T to the power T, which is from vector space Vm over F to Vm star over F into N star over F, then the matrix of linear transformation T to the power T is relative to B ordered basis B1 star and B star, and which is nothing but the matrix A transpose. Okay. Now the columns of the matrix A transpose are nothing but the rows of the matrix A. The matrix A. Actually, it is a transpose, and we know that transpose of a matrix is nothing but here we interchange the rows and columns of the given matrix. Then the corresponding matrix is said to be a transpose of the given matrix. As column, therefore, from this we say that columns of the matrix A transpose are nothing but the rows of the matrix A. So now applying the same reasoning as we have applied on matrix A, then we get from equation 1 we get, here we have to apply the same reasoning on matrix A transpose. Then we get rank of, here your linear transformation is T to the power T. So rank of T to the power T is equal to column rank of matrix A transpose. Okay. Now but column rank of matrix A transpose is nothing but the row rank of a matrix A. So rank of T transpose is equal to row rank of matrix A. Since the columns of the matrix A transpose are nothing but the rows of the matrix A, therefore the column rank of a matrix A transpose is nothing but the row rank of the matrix A. In previous lecture, if V and W are two finite dimensional vector spaces over the field F, then we have proved that the row rank or the rank of matrix the rank of the T to the power T is nothing but the rank of a linear transformation T. That is, in previous lecture we have proved that rank of T to the power T is nothing but the rank of T. So from this, rank of T is nothing but row rank of A. Row rank of matrix A. Do this one as a equation 2. Equation 1 says that rank of linear transformation T is equal to column rank of A, and equation 2 says that rank of linear transformation T is nothing but the row rank of A. As left hand side of both the equations are equal, then right hand side must be equal, which implies from 1 and 2 row rank of A, row rank of matrix A equal to column rank of A. Rank of A. And that is we have to do. So if A be any matrix of order m cross n, then the row rank of a matrix A is always equal to the column rank of a matrix E, and hence the okay. So here we complete our point row and column rank of a matrix. Now we have to see what are the characteristic values of the linear transformation or linear operator. Characteristic value of T. Okay. Let T be a linear operator on a finite on a n-dimensional vector space. That is finite dimensional vector space. N-dimensional vector space V over the field F over the field F. Then the scalar C belonging to field F is called or is characteristic value characteristic characteristic value of linear operator T if there is a non-zero vector alpha belonging to vector space C V alpha belonging to V such that T of alpha equal to C into alpha. So, if T is any linear operator on a n-dimensional vector space, linear operator means the domain and codomain of a transformation is same. So, if T be any linear operator on n-dimensional vector space V over the field F, then the scalar C belonging to field F is said to be a characteristic value of a linear transformation T if there is a non-zero vector alpha belonging to V such that T of alpha is nothing but C into alpha. Then we say that this C is a characteristic value of a linear operator T. Also, if C is a characteristic value of T, then any vector, any non-zero vector alpha belonging to V such that T of alpha equal to C into alpha is called a characteristic vector of linear operator T corresponding to characteristic value C. If T be any linear operator on n dimensional vector space over the field F, then C belonging to field F is called a characteristic value of linear operator T if there is a non-zero vector alpha belonging to V such that T of alpha equal to C alpha. And if suppose this is the definition of characteristic value. If C is the characteristic value of T is known to us, then any non-zero vector alpha belonging to V which satisfies this condition T of alpha equal to C alpha is called the characteristic value of linear operator T with respect to or corresponding to characteristic value C. Okay. The characteristic value are sometimes also called as proper value, eigenvalue, eigen or spectral value or latent roots. So, the characteristic values are sometimes also called as proper value, eigenvalue, or the spectral value, or we can say it as a latent roots. And the column vectors are called proper vector, eigenvector, or spectral vector. Okay. Now we have to see one example depending on this definition. Let T be a linear transformation from or linear operator from R2 to R2 defined by T of xy is equal to x plus y comma 0. So here we have given one linear operator which is from R2 to R2 and which is defined by T of xy is nothing but x plus y comma 0. Now we have to find out the characteristic value and characteristic vector corresponding to that characteristic value. Then from this definition, T of 2 comma 0 is equal to, here value of x is 2 and value of y is 0, which is nothing but by given definition T of 2 comma 0 is nothing but 2 plus 0 comma 0 as y is 0. 2 plus 0 comma 0 which is equal to 2 0. Now we have to find out the characteristic value of T, and if any C belonging to field here is said to be a characteristic value of T if there exists a non-zero vector alpha belonging to V such that T of alpha is equal to C into alpha. So here we have taken alpha as 2 comma 0 as alpha equal to 2 comma 0. So to prove that any C is a characteristic value of this T, we have to prove that T of alpha equal to C into alpha. So here alpha is 2 comma 0 and we have taken T of alpha, that is T of 2 comma 0 is equal to 2 into 0, and which is nothing but T of 2 comma 0 equal to 2 0, and this 2 0 is nothing but your alpha. So here we get T of alpha equal to alpha and coefficient coefficient of alpha is 1. So T of 2 comma 0 is equal to 1 into 2 comma 0, that is T of alpha is equal to 1 into alpha. Therefore C is equal to 1. C equal to 1. C equal to 1 month, it implies that 1 is the characteristic value of T. Okay, characteristic value of linear operator T. Sorry, 1 is the characteristic value of T, and here value of alpha is nothing but 2 comma 0, though this one, and it is not equal to 0. So alpha is a non-zero vector belonging to V such that T of alpha equal to 1 into alpha. 1 is the characteristic value of T, and from definition of characteristic vector, this 2 comma 0 is the characteristic vector, and 2 comma 0 is characteristic vector. Okay, now the set of all characteristic vectors, or sorry, the set of all characteristic values of linear operator T is called spectrum of linear operator. So a set which contains all the characteristic values of linear operator T is called a spectrum of. Now we have to prove one theorem or one result. Let alpha is a characteristic vector of alpha is a characteristic vector of T. Then characteristic vector of T corresponding to characteristic value C. Then K into alpha is a characteristic vector of T corresponding the to same characteristic value C, where K is any non-zero scalar. So here we have to prove that if alpha is a characteristic vector of a linear operator T corresponding to characteristic value C, then we have to prove that K alpha is a characteristic vector of linear operator T corresponding to the same characteristic value C, where K is any non-zero scalar. As here given that alpha is a characteristic vector of T corresponding to characteristic value C. Then from definition of characteristic value, we get T of alpha is equal to C into alpha, and also it is given that and K is any non-zero scalar. Okay. Now we have to prove that K alpha is a characteristic vector corresponding to characteristic value C. Consider T of K alpha. But we know that T is a linear operator. As it is a linear operator, then it goes the linearity property. So which is nothing but K into T of alpha. But from equation 1, T of alpha is nothing but C into alpha, which is nothing but C into alpha, and which is nothing but Kc of alpha, which is nothing but Kc is nothing but Ck of alpha, and which is nothing but C into K alpha. So here we have proved that P of K alpha is nothing but C into K alpha. Therefore, from definition of characteristic value, here T of K alpha is nothing but C into K alpha, which implies that K alpha is the characteristic vector of linear operator T corresponding to the characteristic value C. Therefore, from definition, or this shows that K alpha is the characteristic vector of T corresponding to the characteristic value C, and hence the proof. That's we have to prove now. Next result, if alpha is a characteristic vector of linear operator T, then alpha cannot correspond to or cannot correspond correspond to more than one characteristic value of C. That one characteristic value of linear operator. So here we have to show that if alpha is any characteristic vector of a linear operator T, then alpha cannot correspond to more than one characteristic value of a linear operator T. If possible, suppose that alpha is a characteristic vector of linear operator T corresponding to eigenvalues C1 and C2. C1 and C2. So here we have assumed that alpha is a characteristic vector of T corresponding to eigenvalues C1 and C2. Then by definition of eigenvalue, by definition, T of alpha equal to C1 alpha and T of alpha equal to C2 alpha. Now, as left hand side is equal, then right hand side must be equal, which implies C1 alpha equal to C2 alpha. That is C1 alpha minus C2 alpha is equal to 0, which implies C1 minus C2 of alpha is equal to 0. As alpha is a characteristic vector, then alpha is non-zero, which implies alpha is non-zero, and C1 minus C2 into alpha will be C1 minus C2 of alpha is 0. Then C1 minus C2 must be 0. C1 minus C2 will be equal to 0, which implies C1 must be equal to C2. So, if possible, we assume the contradiction that the alpha is a characteristic vector corresponding to two eigenvalues C1 and C2, then we get C1 will be equal to C2. That is, from this we conclude that, or this shows that if any characteristic vector of T can correspond to exactly one characteristic value of linear operator T. If possible, we assume that alpha is a characteristic vector of T corresponding to two eigenvalues C1 and C2. Then we get C1 must be equal to C2. From this, we conclude that any characteristic vector of a linear operator T is corresponds to exactly one characteristic value of characteristic value of linear operator T, and which is the required result. Okay. Now, next one. Let P be a linear operator on finite dimensional vector space. Finite dimensional vector space V. Vector space V, and let C is a characteristic value of linear operator T, then the set WC, which contains all alpha belonging to vector space V, such that T of alpha is equal to C alpha, and we have to prove this is a subspace of vector space. So here, if T be a linear operator on finite dimensional vector space V, and let C is the characteristic value of linear operator T, then the set WC, which contains all alpha belonging to V, such that V of alpha equal to C of alpha, is a subspace of V. So we have to prove that WC is a subspace of V. That is, here we have to prove that WC is closed under the operations which are defined on vector space V, or we have to prove that WC is itself a vector space. It is easy to prove that WC is closed under the operations which are defined on the vector space V. Let alpha and beta be any two members of WC and A belonging to F be any scalar. Okay, as alpha and beta belonging to WC, then according to their definition, T of alpha is nothing but C alpha and T of beta is equal to C into beta. Now we have to prove that WC is a subspace of V. That is, we have to prove that. That is to prove that A alpha plus beta is also belonging to WC, and A alpha plus beta is belonging to WC if and only if P of A alpha plus beta is equal to C into A alpha plus beta. Then this A alpha plus beta is belonging to WC. It is from given set WC. Now consider T of A alpha plus beta. Okay, as T is a linear operator, therefore T of A alpha plus beta is nothing but A into T of alpha plus T of beta. But from this equation 1, T of alpha is nothing but C into alpha and T of beta is nothing but C into beta. So which is C into alpha plus C into beta. Sorry, here A into C alpha plus C beta, which is nothing but AC into alpha plus C into beta, which is nothing but CA of alpha plus C beta, CA alpha plus C beta, and which is nothing but C into A alpha plus C into beta. Now take C common, we get T of A alpha plus beta is equal to C into A alpha plus beta. Now from the given say the WC, this A alpha plus beta is belonging to WC, which implies A alpha plus beta is belonging to WC. Okay. Now as A alpha plus beta belonging to WC, then WC is closed under the operations which are dependent on the vector space V. Then by definition of subspace, WC is a subspace of V. WC is subspace of, and hence the name. There is one node. This set WC is nothing but the set of all characteristic vectors of linear operator T corresponding to characteristic value C. See what is WC? WC is nothing but all alpha belonging to V such that T of alpha equal to C alpha. Then by the definition of characteristic vector, is nothing but if C be any characteristic value of linear operator T, then any non-zero vector alpha belonging to V such that T of alpha will be equal to C alpha is called a characteristic vector of T corresponding to the characteristic value C. As here WC is nothing but the alpha belonging to V such that T of alpha will be equal to C alpha, where C is the characteristic value of T. Then by definition of characteristic vector, this WC is nothing but the collection of characteristic vectors of a T corresponding to characteristic value C. Okay. And we know that zero vector is always the characteristic vector of any linear operator, and it includes the zero vector also, and it includes the zero vector also, since zero vector is always a characteristic vector. Now in other words WC is the null space of the linear operator T minus Ci, where I is the identity operator. How? Let us see. WC is nothing but as WC is equal to all alpha belonging to such alpha belonging to V such that P of alpha will be equal to C alpha, which is nothing but alpha belonging to V such that P of alpha is equal to C into I of alpha, where I is the identity operator, which implies which is nothing but alpha belonging to G such that P of alpha minus Ci of alpha, which is equal to 0. So which is nothing but alpha belonging to G such that P minus Ci of alpha is equal to 0. Then by definition of null space of any operator T minus Ci is nothing but it includes all alpha belonging to vector space V such that P of minus T minus Ci of alpha will be equal to 0. Then from this definition, WC is nothing but actually the null space of a linear operator T minus Ci. And here this subspace WC. In previous result, we have proved that WC is a subspace of V. WC of V is called a characteristic space of characteristic value C of a linear operator T. Okay. There is one important remark. C is the characteristic value. C is the characteristic value of T if the subspace or the characteristic space WC is different from zero subspace. From zero subspace. Zero subspace. Since for characteristic vector we require one alpha which is not equal to 0. So if any C is the characteristic value of T, if we get one, that is WC contains one vector which is different from 0, that is WC contains at least one vector. Okay, thank you for watching the lecture.